Okay, at the risk of seeming repetitive, I'm going to write the 5 steps that I want you to do to approach these problems. And step 1 is read the question. Step 2 is read the question again. Step 3 is draw as much as you can. Step 4 is write down what you know and then start solving, going from the known to the unknown. Right, so let's read this question together. A student used the equipment shown to investigate the behavior of a spring. We've got a meter rule, we've got masses, we've got a spring, and then you've got a clamp and stand. Yeah. The student recorded the position of the spring on the meter rule for increasing loads. He plotted the graph shown for the loading and unloading of the spring. Okay, so you can see this. The student continued to increase the load until the spring exceeded the elastic limit at point L. State the significance of point K. Okay, explain the significance of point L. The graph for the unloading of the spring is also shown on the axes. Suggest why the unloading graph has a different gradient to the loading graph. Okay, that's all we'll do for now. So let's read it again. A student used the equipment shown to investigate the behavior of a spring. Fine, yes, he's going to put some masses on there, which are going to stretch the spring. Right. The student recorded the position of the spring on the meter rule for increasing loads. He plotted the graph shown for the loading and unloading. The loading is the dark line. Okay, so he's put 1, 2, 3, 4, 5. Okay, a few bunch of newtons on there, and he's measured the extension. The student continued to increase the load until the spring exceeded the elastic limit at point L. Okay, elastic limit at point L. State the significance of point K. Well, point K, let's have a look at this then. Okay, we don't need to draw any additional stuff on this one, step 3. We can just put some notes in onto the diagram. But this is a straight line. So what you're always looking for on this type of question is a straight line part, a part which is no longer straight, starts to curve, no longer straight. We don't know exactly where this point L will be, which is why they told us this is the elastic limit. That means if you increase it in extension beyond that point, it will no longer return to its original length. So that means when you take off the force, there will be an extension. So it will actually have moved as a result of this loading, this particular experiment. It will have increased its natural length by 3 centimeters. Okay, so the significance of point K, well, we can see this is the end of the straight line part. So that is what we would call the limit of proportionality. And the limit of proportionality is the end of Hooke's law being obeyed. And probably you'd want to say, for correctness, you'd want to say that the extension and the load were proportional. So the force is proportional to the extension. You might even want to say it as F is equal to Kx. You might even want to say it as F is equal to minus Kx, because the force, the stretching force, is opposite. The stretching force, well, you have to put some force to stretch it, but the actual force or the load that's proportional to the extension is the force in the spring, which is restoring it to its original length, which is going to be going the opposite direction to the increase of length, which is why we tend to call it a restoring force. It's complicated for you to see that, I agree, because what we're saying is, well, surely the force that we're putting on the load is in this direction. Yes, but at any point, the thing is not accelerating. So if it's not accelerating, that means that the load here, the force, the weight in newtons, is balanced exactly by the restoring force, which is what we call this F. Okay, so limit proportionality. Explain the significance of point L. Well, they tell us that point L is the elastic limit. There's 2 marks for this. So you're going to have to say a little bit more. So you're going to have to say something like, beyond this point, the wire will not return to its original length. When released from tension, when load is removed. Okay, so that's pretty basic. It's not very difficult. The graph for the unloading of the spring is also shown on the axes. Suggests why the unloading graph has a different gradient to the loading graph. Well, this is interesting. Different gradient. What this is really going to mean is, okay, so what is the gradient? And this is quite a clever question. So first of all, let's have a look at what the gradient is. Well, the gradient is the slope. So this slope is not quite, and we can draw it. I can show this. So this will be quite nice, actually. I can show you this one, and if I move this, I should be able to. Oops. What I really want to do is just move it a tiny bit. Okay. So if I then move this, you notice that it's not the original gradient anymore. The original gradient is different. And this gradient is not as steep. So let's go back to what a gradient is. Let's start with what we know. What is a gradient? A gradient is equal to the change in y divided by the change in x. So the change in y is equal to the change in F, the force in newtons, divided by the change in length, extension, which is in centimeters. So the gradient, which we can call m if we like, is equal to delta F over delta x. Okay, now that looks suspiciously like this equation, F equals kx. Right, okay. So the gradient, if we rearrange this equation, and I'm going to write it down here actually. So the gradient equals the delta F divided by delta x. We compare with F equals kx. We can say what? This is the gradient equals k, which is the spring constant. And what's happened, because we've distorted the spring constant is now different. So suggests why the unloading graph has a different gradient to the loading graph. Right, so the gradient equals k. So for the spring constant has changed, and it's only 1 mark, so they don't want you to do a big explanation. What you could say with that is, as a result of it being distorted, it's now a different length. So it's got a different length but the same atoms, so you would expect it to have a different behavior from now on. Okay, we're going to continue. A second student repeated the investigation but forgot to subtract the original length of the spring from his measurements. So if you notice, this graph is extension, and the extension is 0 when the force is 0. But if you forgot to subtract, that means your numbers are going to be higher. So we don't know what it's going to be exactly, but let's say the original length of the thing was, say, 10 centimeters. It means your graph is going to start from about here, and it should look the same. should look the same more or less as that original one, but it will have, instead of the extension being starting at 0, it will be starting somewhere like plus 10. So you come along to something like this, and then you draw the same shape graph, which will be something like that. And you'd want it to do the same thing, so you want it to be the same shape. So you want it to kind of do something like this for just the loading of the spring. So just the same shape, but this distance, this is the original length, is here. Okay, let's have a look at the second part of this. A third student repeated the investigation using 2 new springs connected in series, as shown. The springs were identical to the spring used in the original investigation. Explain why the spring constant for this arrangement of the springs would be half that for one spring. Okay, so again, let's read it twice. A third student repeated the investigation using 2 new springs connected in series as shown. The springs were identical to the spring used in the original investigation. Explain why the spring constant for this arrangement of the springs would be half that for one spring. Okay, so spring constant, if we go F equals Kx, the spring constant K is equal to the change in F divided by the change in X, which is the gradient. But what's more interesting now, I guess, is how much force produces how much extension. Well, let's have a look at this. Let's think of it just from here, just the bottom half. This will be exactly the same. So this is F is equal to Kx, which means if you have, let's use some numbers if you like. So if you have a load of maybe 2 newtons there, you're going to get an extension of about 2 centimeters. So here you'll get 2 newtons will give you an extension of this spring of about 2 centimeters. But this spring is the same. So a load of 2 newtons would also give you an extension of 2 centimeters on this bit. So this whole thing would give you an extension of 2 centimeters. And this whole thing would also give you an extension of 2 centimeters. If we ignore the masses of the spring, because technically the mass of the spring would mean that the load on this is a little bit more than 2 newtons. So what we're getting is for the same load, we get twice the extension. So we're getting twice the extension. So if you think of it on a graph, same load, so this is the original one, something like this. So this is the extension, this is the force, the load, and now we're getting twice the extension. So we're going to get, so instead of it being here for 2 newtons and 2 centimeters, it'll be about 4 centimeters. So we get this, twice the extension for the same load. And this is the 1 time the extension. So what that means is the gradient, if you look on this, is half. So the gradient of blue line equals half original gradient. If the gradient is half, that means the spring constant is also half, because the spring constant is the gradient. So therefore, spring constant of this arrangement is also half of a single spring. There you go, 9 marks. Right.